All right, Feynman's lectures, huh? You guys weren't kidding around with this deep dive request. Talk about going big brain. But hey, we love a challenge, so today we are diving headfirst into the world of physics pre and post 1920s, just as Feynman laid it out for us.
And let me tell you, it's a wild ride. We're talking a complete upheaval in how we understand the universe, like at its very core.
Bro, almost like humanity thought it was playing checkers this whole time, but then bam, the universe pulls out a whole chessboard we never even knew existed.
Perfect analogy. And Feynman, being the master explainer that he was, uses that very analogy, the chess game, to show how physicists actually do physics. Picture it, the universe is a giant chessboard, right? And we're like, these curious kids peering over the edge trying to figure out the rules just by watching the game.
So we're not just moving our own pieces, we're trying to make sense of the universe's moves. I like it.
Exactly. Looking for those patterns, testing predictions, seeing if the universe plays by the rules, so to speak. And like any good investigation, we start small. Isolate a simple scenario, two particles interacting, almost like isolating two pawns on our giant chessboard.
Okay, so start small, find those basic moves, but it's when those moves don't go as planned, that's when things get interesting.
Right.
Totally. Those head-scratching moments when the universe throws you a curveball, that's where the real breakthroughs happen. It's like suddenly, wait, pawns can move backwards. Those unexpected observations, that's what makes us rethink the entire game.
Okay, I see where you're going with this. So to really grasp this whole quantum revolution, we've got to rewind a bit and get a sense of the playing field before everything changed. Exactly. So picture this pre-1920s physics. They thought they had a pretty good handle on things. It was all very orderly. The universe was this grand stage set in 3 dimensions, and time was ticking along nice and steady like a metronome.
And the actors on this stage, those tiny bits of matter, the atoms.
Right, and everybody thought these atoms, these particles, they followed Newton's laws. Inertia. An object in motion stays in motion unless...
Unless a force acts on it. You got to give
Yeah.
those particles a little nudge if you want them to change course.
Exactly. And back then, there were two main forces running the show. First, you've got gravity, keeping our feet on the ground, and the planets in check.
Always there, the great unifier.
Then you've got the electromagnetic force. Way stronger than gravity, but a bit more of a homebody. Likes to act over shorter distances. This is the force behind electricity, magnetism, and the very structure of atoms themselves.
Hold on, atoms. You're telling me the electromagnetic force is the reason atoms even hold together.
Hmm.
But atoms have positive and negative charges inside them, right? Those protons and electrons, shouldn't they just collapse in on themselves if they're constantly attracting each other?
And that's where things get really mind-bending with this concept of the electric field. You see, it's not just a simple game of tug-of-war between charges. Each charge actually creates this condition in the space around it, this invisible something. We call it the electric field.
Whoa, okay. So instead of directly pulling on each other, the charges are interacting with this field. It's like playing on a warped chessboard, where the squares themselves can influence how the pieces move.
That's a fantastic way to put it. The electric field, it's just as real, just as fundamental as the particles themselves. And get this field, it's not just sitting there, it can fluctuate, it can carry energy.
Okay, yeah, definitely getting some mind-bending vibes now. How does that even work?
So imagine you wiggle a charge, like jiggling a chess piece on our board, right?
Yeah.
This creates these disturbances in the electric field around it, and these disturbances, they spread outward, like ripples in a pond. We call these ripples electromagnetic waves.
Wait, are you saying light is an electromagnetic wave?
Bingo. And it's not just light. We're talking about a whole spectrum of electromagnetic waves, each with its own, let's say, vibration speed. You've got radio waves, microwaves, the visible light we see, even X-rays and gamma rays, all part of this electromagnetic family.
Wow, I never thought of a rainbow as just this tiny sliver of this massive electromagnetic spectrum. That's incredible. So physicists back then, they thought they had it all figured out. They had their space-time chessboard, their particle pieces, even these invisible fields influencing the game.
That's what they thought. Little did they know, the universe had a few more surprises up its sleeve. They were about to discover that the rules of the game were far stranger than they could have imagined.
So we've got our nice, neat chessboard all set up, our pieces, the rules.
Yeah.
Even those invisible fields shaking things up a bit, and then boom, quantum mechanics enters the scene and flips the whole table over.
Uh-huh. Yeah, you could say that. It's like around the 1920s, physicists started noticing some really strange things. Especially with those tiny particles, the subatomic world, things just weren't quite adding up with the old rule book.
So it's more than just pawns moving backward now. We're talking completely new game. So how did they even start to wrap their heads around this whole quantum weirdness?
Well, it was a whole new way of thinking about the universe. One of the biggest game changers was this thing called Heisenberg's uncertainty principle.
Oh yeah, I've heard of that one, but it always seemed, well, a bit uncertain to me. What's the basic idea?
Imagine you're trying to pinpoint the exact location of one of those pawns on our chessboard, right? But the pawn's moving. You can maybe get a general idea, but the more you try to nail down its position, the less sure you are about how fast it's going, which direction it's headed.
Because the very act of looking at it messes things up.
Sort of. It's this weird thing where, at that tiny scale, you can't know both a particle's position and its momentum, how fast it's moving, with perfect accuracy. The more you know about one, the fuzzier the other one gets. It's like a fundamental limit to what we can know.
Okay, yeah, my brain's already doing backflips. But how does this explain why those atoms don't just implode? I mean, we were just talking about how that electromagnetic force should be pulling those electrons right into the nucleus.
And that's where the uncertainty principle throws a wrench in things. If an electron got too cozy with the nucleus, its position would be so clear that its momentum would go haywire, like it suddenly got a jolt of energy.
So it's like that electron would just shoot right back out.
Exactly. That uncertainty principle, it's like a built-in safety mechanism for atoms. It's this constant push and pull between the electromagnetic force trying to reel them in and this inherent uncertainty in their momentum keeping them at bay.
Whoa, so this isn't just some abstract physics thing. It has real-world consequences, like literally shaping the building blocks of matter. But if we're saying we can't really know both a particle's position and momentum at the same time, doesn't that mean the universe is inherently unpredictable?
That is one of the most mind-blowing things about quantum mechanics. It throws in this element of randomness, of chance, that completely changes the game from the old way of thinking.
It's like the universe is playing with loaded dice, even if we think we know the rules.
Exactly. We can't know for sure what's going to happen, even if we think we figured out all the rules. The best we can do is calculate the probabilities of different outcomes.
So even with a perfect understanding of the game, the universe still has a few tricks up its sleeve. This cosmic chess match just got a whole lot more interesting. So quantum mechanics kind of throws this whole idea of absolute certainty out the window. But doesn't it also open up these new, unexplored regions of the universe? We've gone from this neat and tidy chess game to something much stranger, much more complex.
Absolutely. And with this new quantum era came, well, a whole bunch of new pieces on that chessboard we were talking about. Particles that physicists had never even dreamt of.
This is what Feynman calls the particle zoo, right? It's like we need a bigger board, but we have no clue what the rules are for these new pieces.
Huh. That's a great way to put it. And it wasn't just theoretical either. By the 1960s, physicists were using particle accelerators, these massive machines, to smash atoms together at crazy speeds. And the result? A whole menagerie of new and exotic particles.
Okay, so how do you even start making sense of that? It sounds overwhelming.
It was. But amidst all that chaos, there were flickers of order. One of the biggest breakthroughs, quantum electrodynamics, or QED for short. This theory brought together quantum mechanics and our understanding of electromagnetism.
QED sounds intense. What's so special about it?
Well, for one, it's incredibly accurate. QED explains exactly how light and matter interact at the most fundamental level. And get this, it accounts for a mind-boggling range of phenomena, why metals conduct electricity, how plants use sunlight, even down to the nitty-gritty of chemical reactions.
So it's not just about these exotic particles. It's about understanding the stuff we see every day in a whole new light. Pun intended, of course.
Exactly. But what's even more impressive, QED actually predicted the existence of antimatter long before we even observed it.
Antimatter. Okay, now we're going full sci-fi. Isn't that like Star Trek territory?
Right. Sounds crazy, but it's very real. Antimatter, it's made up of these particles that are like mirror images of regular matter. So take the electron, for example. Its antiparticle twin is called the positron. Same mass, but the opposite charge.
And what happens when matter and antimatter meet?
So let's just say it's not pretty. They annihilate each other. Poof, gone in a flash of pure energy.
That's both amazing and kind of terrifying. So with all these new particles popping up, How did physicists even begin to organize them? Did they ever find, like, a quantum periodic table?
Oh, they were definitely searching for one. They started noticing patterns in relationships, kind of like Mendeleev did with those elements, right? For example, they found particles could be grouped based on their mass, their charge, and even this new strange characteristic they called, well, strangeness.
Strangeness, like how weird they are.
Well, not exactly. It's a bit more complicated than that. Strangeness is this quantum property. Basically, it describes how particles interact with something called the strong force, the force that glues those protons and neutrons together inside the nucleus.
Right, the strong force. That's the one that's even stronger than the electromagnetic force.
Mm.
So even with QED and all these fancy classification schemes, we still had mysteries to solve within the nucleus itself.
Oh, tons. We still don't fully understand the true nature of the strong force. And then there's a muon. Essentially, it's like a heavier electron, but nobody knows why it exists. These are questions that still keep physicists up at night.
It's kind of humbling, you know? We've learned so much about how the universe works, and yet there's still so much we don't know, even at the most fundamental level.
That's the beauty of science. It's this never-ending journey. Feynman's lectures, they gave us an incredible foundation to build on, but they also opened our eyes to just how much more there is to explore.
It's like we've only just started to uncover the tip of the iceberg.
Exactly. And who knows what incredible discoveries await us as we continue to explore. The universe is full of surprises, with new rules waiting to be discovered, and maybe even some moves we can't even imagine yet.
No doubt. Well, on that note, a huge thank you to you for joining us on this incredible journey through the wild world of physics. It's clear that even with all the advances we've made, the universe still holds plenty of mysteries just waiting to be unraveled. Until next time, keep those brains buzzing.